Welcome to our channel. In today's video, we will continue on exploring chemistry. The periodic table is a fundamental tool in chemistry, organizing all known chemical elements. Elements are arranged based on their atomic number, electron configuration, and recurring chemical properties. This visual representation helps us understand the relationships and patterns between elements. The periodic table reveals important information about each element, such as its reactivity, state of matter, and atomic structure. Understanding the periodic table is crucial for chemists, scientists, and anyone studying the composition and behavior of matter. The periodic table continues to evolve as new elements are discovered, expanding our knowledge of the building blocks of the universe. The periodic table is a fundamental tool in chemistry, providing a systematic organization of all known elements. It serves as a universal language for chemists, allowing them to communicate and understand chemical phenomena across different regions and disciplines. The periodic table provides valuable information about each element's properties, reactivity, and behavior in chemical reactions. By studying the periodic table, chemists can predict the properties of unknown elements and design new materials with desired characteristics. The periodic table has a long and fascinating history, tracing back to early attempts by chemists to categorize and classify the elements. In the 18th century, chemists began grouping elements based on their properties, laying the groundwork for later developments. In 1829, Dobereiner identified groups of 3 elements with similar properties, known as Dobereiner's triads. In 1869, Mendeleev arranged the elements by atomic weight, revealing periodic trends and creating the first modern periodic table. Over time, the periodic table has been refined and updated as our understanding of atomic structure and element properties has advanced. Today, the periodic table is an indispensable tool for chemists, representing our comprehensive knowledge of the elements and their relationships. Atoms are the fundamental building blocks of all matter. The atom has a dense, positively charged nucleus at the center. The nucleus contains protons and neutrons. The number of protons determines the element's atomic number. Electrons orbit the nucleus in specific energy levels or shells. The arrangement of electrons determines the atom's chemical properties. The diagram shows a visual representation of the atomic structure, with the nucleus at the center and the electron shells surrounding it. The colorful, realistic depiction helps illustrate the key components of the atom. The atomic number is a fundamental property of an element. It's the number of protons in the nucleus. This determines the identity of the element. For example, hydrogen has 1 proton, helium has 2 protons, and so on. The atomic mass is the average mass of an atom of an element, measured in atomic mass units, AMU. The atomic mass is primarily determined by the number of protons and neutrons in the nucleus. This detailed diagram shows the key components of an atom, the protons, neutrons, and electrons, with the atomic number and mass highlighted. Periodic trends are important patterns we observe in the properties of elements as we move across the periodic table. Today we'll discuss 3 key periodic trends: electronegativity, ionization energy, and atomic radius. Electronegativity is the ability of an atom to attract electrons in a chemical bond. It increases from left to right and bottom to top of the periodic table. Ionization energy is the energy required to remove an electron from an atom. It also increases from left to right and bottom to top. Atomic radius is the distance between an atom's nucleus and its outermost electron shell. This increases from right to left and top to bottom of the table. Understanding these trends helps us predict and explain the chemical behavior of elements. Electronegativity is a measure of how strongly an atom attracts electrons when forming a chemical bond. It's a fundamental property that influences the type of bond formed and the chemical properties of molecules. An element's electronegativity is affected by its atomic number, number of electron shells, and effective nuclear charge. Elements with higher electronegativity attract electrons more strongly, while those with lower electronegativity are more likely to lose electrons. Understanding electronegativity is key to predicting and explaining the behavior of atoms and molecules. Ionization energy is the minimum energy required to remove an electron from a gaseous atom or ion in its ground state. The first ionization energy is the energy to remove the first electron, The second is the energy to remove the second electron, and so on. Ionization energy generally increases across a period and decreases down a group in the periodic table. Factors affecting ionization energy. Atomic radius. Smaller atoms have higher ionization energies. Nuclear charge. Higher nuclear charge leads to stronger attraction to electrons and higher ionization energies. Electron shielding. Electrons in inner shells shield outer electrons from the nucleus, lowering ionization energy. The image on this slide shows the atomic radius of various noble gases, measured in picometers (pm). Atomic radius is the distance between the nucleus of an atom and its outermost electron shell. The atomic radius generally increases as you go down a group in the periodic table, but decreases as you go across a period. The atomic radius is an important factor in determining the chemical properties of elements. The atomic radius is affected by the element's electron configuration, nuclear charge, and number of electron shells. The noble gases shown here, helium, neon, argon, krypton, xenon, and radon, have increasing atomic radii as you go down the group. Understanding atomic radius helps us predict and explain the behavior of elements in chemical reactions and processes. Electron configuration describes how electrons are distributed within an atom, following specific rules based on quantum mechanics. Understanding an element's electron configuration helps predict its chemical reactivity and the types of bonds it can form. Electron configuration also explains periodic trends in the periodic table, like ionization energy and electronegativity. This is a foundational concept in chemistry that is crucial for understanding atomic behavior and chemical bonding. Valence electrons are the electrons in the outermost shell of an atom, and they're the ones involved in chemical bonding. The number of valence electrons an atom has determines its chemical properties. Elements in the same group of the periodic table have the same number of valence electrons. Valence electrons play a crucial role in chemical bonding. They are involved in the formation of ionic bonds, covalent bonds, and metallic bonds. The tendency of atoms to gain, lose, or share valence electrons drives these interactions. Understanding valence electrons is key to understanding the fundamental behavior of atoms and how they interact with each other to form compounds. The periodic table is divided into three main categories: metals, nonmetals, and metalloids. Metals are generally shiny, malleable, and good conductors of heat and electricity. They tend to lose electrons and form positive ions. Nonmetals are typically dull, brittle, and poor conductors of heat and electricity. They tend to gain electrons and form negative ions. Metalloids exhibit properties of both metals and nonmetals. They are often semiconductors and have intermediate conductivity. This slide provides a high-level overview of the key characteristics of these three groups of elements on the periodic table. Groups are vertical columns on the periodic table. Elements in the same group have similar chemical properties. This is because they have the same number of valence electrons. Periods are horizontal rows on the periodic table. Elements in the same period have the same number of electron shells. As you move across a period, the atomic number increases. The elements become less metallic as you move across a period. The alkali metals are a group of highly reactive metals that make up group 1 of the periodic table. They are all soft, silvery white metals that react violently with water, producing hydrogen gas. Their reactivity increases as you go down the group, with the most reactive being the element francium. Alkali metals have a single valence electron, making them very eager to lose that electron and form a +1 cation. This gives them excellent conductivity of heat and electricity. The image shows a shiny metal sphere, representing an alkali metal with an orange flame at the top, symbolizing the reactivity of these elements. The alkaline earth metals are a group of highly reactive metals that have a shiny, silvery appearance. These metals are so reactive that they will actually react with water, producing hydrogen gas and a hydroxide solution. When burned in air, the alkaline earth metals release a lot of energy and produce a bright flame. This property makes them useful for creating colorful displays and special effects in fireworks. Overall, the alkaline earth metals are very reactive and have a number of interesting chemical properties. Transition metals are a group of elements found in the D block of the periodic table. They are known for their ability to form colored compounds and exhibit variable oxidation states. Many transition metals play crucial roles in biological processes. Iron is essential for hemoglobin. Cobalt is a key component of vitamin B12. Zinc is found in many important enzymes. The periodic table image highlights the D block where the transition metals are located. The periodic table is a complex and fascinating representation of the elements that make up our world. Today we'll be focusing on two unique series of elements found at the bottom of the table, the lanthanides and actinides. These inner transition elements share similar chemical properties, which can make them challenging to separate and study. The lanthanides are all metallic elements found in the sixth period of the table. The actinides are radioactive and synthetic, found in the seventh period. Understanding these two series is crucial for many scientific and technological applications. I'll dive into more detail about their unique characteristics and importance in just a moment. Halogens are a group of highly reactive nonmetal elements in the periodic table, located in group 17. Halogens exist as diatomic molecules in their elemental state, meaning two atoms of the same halogen element are bonded together, such as chlorine, Cl2. Halogens have numerous industrial applications, including the production of plastics, pesticides, and pharmaceuticals. They also play important roles in biological systems. The halogens' high reactivity and ability to form compounds with other elements make them versatile and widely used in various industries and processes. Noble gases are a group of colorless, odorless, and highly unreactive elements found in trace amounts in the atmosphere. They are known for their inert nature, meaning they do not readily participate in chemical reactions under standard conditions. Neon is commonly used in lighting, such as in neon signs, due to its bright red-orange glow when electrically excited. Argon is used in welding and as a protective gas in manufacturing processes to prevent oxidation. Krypton is used in high-intensity lamps and lasers, where its unique properties make it useful for specialized lighting applications. Xenon is used in flash lamps and high-pressure arc lamps, taking advantage of its ability to emit intense light when electrically stimulated. Metals are generally very reactive, especially the alkali and alkaline earth metals. They readily lose electrons to form positive ions. Nonmetals tend to be reactive as well, as they gain electrons to form negative ions. The halogens are particularly reactive nonmetals. Water can react with many metals, especially in the presence of oxygen, forming metal oxides and releasing hydrogen gas. Many chemical reactions involve the transfer of electrons, known as oxidation-reduction reactions. This electron transfer drives the reactivity we see in chemicals. The reactivity of different elements is a key concept in understanding chemical behavior and interactions. The periodic table is a powerful tool for understanding chemical bonding and reactivity. Key periodic trends like electronegativity, ionization energy, atomic radius, and electron configuration all play crucial roles in determining how atoms will bond. Electronegativity measures an atom's ability to attract shared electrons in a bond. Higher electronegativity leads to more polar bonds. Ionization energy is the energy required to remove an electron from an atom. Lower ionization energies make it easier for atoms to form cations and ionic bonds. Atomic radius affects bond lengths. Larger atoms form longer bonds, while smaller atoms form shorter bonds. Electron configuration determines the number of valence electrons available for bonding, which in turn influences the type and strength of chemical bonds. Understanding these periodic trends provides valuable insights into the fundamental nature of chemical bonding. Atoms have different sizes due to the number of electron shells and the strength of the attraction between the nucleus and electrons. Ionization energy is the energy required to remove an electron from a gaseous atom, which depends on the atom's size and nuclear attraction. Electronegativity is an atom's ability to attract electrons in a chemical bond, influenced by factors like number of protons and distance of valence electrons from the nucleus. Electron affinity is the energy change when an electron is added to a neutral atom, related to the atom's tendency to gain electrons and form negative ions. Periodic trends are important in understanding the reactivity and behavior of elements. Electronegativity is the ability of an atom to attract shared electrons in a bond. Higher electronegativity means the atom more strongly attracts electrons. Ionization energy is the energy required to remove an electron from an atom. Higher ionization energy means the atom holds onto its electrons more tightly. Atomic radius is the size of an atom, measured as half the distance between two adjacent atoms. Atoms get smaller as you go across a period, row, and larger as you go down a group, column. Electron affinity is the energy released when an atom gains an electron to form a negative ion. Higher electron affinity means the atom more easily accepts an extra electron. The periodic table is a fundamental tool in chemistry and materials science, allowing us to understand chemical reactions and design new materials with predictable properties. It's also essential for developing new electronic components, semiconductors, and energy storage solutions, driving technological advancements. In biochemistry and medicine, the periodic table helps us understand the role of elements in biological systems, aiding in the development of pharmaceuticals, diagnostic tools, and the study of disease mechanisms. Finally, the periodic table is critical for environmental science, helping us study pollution, develop sustainable technologies, and address climate change. The periodic table is a fundamental tool for understanding chemistry, but it can be intimidating for some learners. Incorporating fun, interactive puzzles, and games into the learning process can make the periodic table more engaging and memorable, especially for children. Puzzles that require assembling the elements or identifying their properties can help reinforce key concepts in an enjoyable way. Games that involve matching elements, answering trivia, or exploring the table's patterns can stimulate critical thinking and curiosity about the periodic system. By making the learning experience more dynamic and hands-on, these types of activities can inspire a lifelong fascination with chemistry and the natural world. The periodic table is more than just a chart. It's a powerful tool used across many fields. Chemists rely on it to understand chemical reactions and predict properties of substances. Engineers use it to design materials with specific characteristics. Doctors use it to understand how medications work and how to treat diseases. Even farmers leverage the periodic table to optimize crop yields and soil health. The periodic table is a versatile and essential tool that has applications far beyond the classroom. The periodic table is a powerful tool for understanding the elements that make up our environment and how they interact. Elements like carbon, nitrogen, and oxygen are essential for life on Earth. They are the building blocks of living things. However, some elements can be harmful to the environment when released in excess, like mercury and lead, which can contaminate water and air. The periodic table also helps us understand the scarcity of certain elements, which is crucial for sustainable resource management. It provides insights into the role of greenhouse gases like carbon dioxide in climate change, which is a critical environmental issue. The periodic table is essential for understanding the properties of elements used in a variety of important technologies. Electronics like semiconductors, transistors, and other components rely on the unique properties of elements from the periodic table. The properties of elements dictate the characteristics of materials like metals, ceramics, and polymers, which are critical for technological advancements. The periodic table helps scientists develop new battery technologies, such as lithium-ion batteries, for efficient energy storage. Understanding the atomic structure and properties from the periodic table is crucial for manipulating materials at the nanoscale in nanotechnology. The periodic table is a fundamental tool in drug discovery, as it helps scientists understand the properties of elements and how they interact with biological systems. This knowledge allows scientists to design and synthesize new drugs that can treat diseases more effectively. Radioactive isotopes derived from the periodic table are also crucial for medical imaging techniques like PET scans, which allow doctors to visualize and diagnose various conditions, improving patient care. The periodic table is essential in both drug discovery and medical imaging, two important areas that have a significant impact on human health and well-being. The periodic table is a powerful tool for understanding how elements store, release, and enable the production of various forms of energy. Energy storage is a key property of many elements. We'll explore how the periodic table helps us understand this. Elements like uranium and thorium are essential for nuclear energy generation, which is a major source of power. Renewable energy technologies like solar and wind rely on elements like silicon and copper. The periodic table reveals why these are so important. Understanding the properties of elements, as shown in the periodic table, helps us optimize energy efficiency across many applications. This slide provides an overview of how the periodic table is crucial for understanding energy in its many forms: storage, production, renewables, and efficiency.